pretty good.
I'm Verran, and today I'll be talking to you about some areas of nanotechnology. I'm not going to cover all the areas. I'm going to cover some of the areas that mainly pertain to technology, not biology. Nanotechnology is like the elimination elimination of matter on the atomic and molecular scale. You know, moving the building blocks of life around. We were doing it back across the medieval ages with the window panes on the churches. You know, that's how they melt the metal down to where it was so small. Gold can make purple and copper green and things like that. Let's start with nanobots. Making robots to help us kill cancer cells, homing missiles that just go straight to the cancer cell and ignore all the healthy cells. Who knows what age we're in? What age of metal we're in? The steel age. Everywhere you see is steel. And there's two things that made steel: carbon and iron. Well, I'm talking about carbon there. Carbon can make graphite, glass, carbon, charcoal, diamond, and carbon fibers. Diamond is strong but not very malleable. You can't shape into what you want. Graphite, pencil, lead can be created into graphene. And graphene is really an atom thick layer of graphite, in which sometimes you can make it into carbon nanotubes. Who's heard of carbon nanotubes? Yeah. Graphite is what we use to write every day. Very cheap, and carbon is the most third abundant element in the air. So, and it can become a harmful gas. So we can use that by chemical means, extract that from the air. Single layer of graphite. Let's watch a little video.
Should be like this? I just thought they'd be smaller. I'm right. They're about 1 billion times smaller. Nanotubes are made of carbon atoms arranged in a rolled-up chicken wire-like structure. Besides nanotubes, there are other forms of pure carbon, like diamond, and graphite, the stuff of pencil lead. Nanotubes get their strength from the extremely strong bonds between carbon atoms.
These carbon nanotubes can have spectacular mechanical properties, spectacular strength, and very high toughness.
And you make them here in this very lab?
Yes, we do.
Ah, so this is where it all happens.
This is where the process begins.
And guess what? It's not even that difficult. Here's all you need. 1. A smooth surface with a thin layer of catalyst, a chemical that helps jumpstart the tubes. 2. A special mix of gases full of carbon atoms. And 3. This furnace, which, by the way, is really, really hot.
How much heat is it in there?
Right now it's around 800 Celsius.
That's about 1,500 degrees Fahrenheit.
Wow.
And I could nuke a pizza in like 5 seconds in there.
Yeah. And open more.
Oh man, that is blasting heat. Oh, I see the little
black wafer in there, that's it?
Yep.
That's nanotubes?
Yes, actually.
Wow, that is very cool. Baking away in there.
Wow, it's like a nuclear tanning bed. After just a few hours, the wafer is covered with a thick black fudge. So it looks just like a piece of black velvet. So if I were to really look in close to that, what would I see? What's it really look like under the microscope?
Well, we call this array of carbon nanotubes a nanotube forest.
The name is apt. Each nanotube looks like a tall, thin bamboo tree, hollow inside. So thin that if you could scale one up until it was 1 inch wide at the base, the top of it would reach 2 miles into the sky. Now picture nanotubes by the billions, all standing shoulder to shoulder, and you have one of Ray's nanotube forests.
There are, in fact, about 200 billion of the carbon nanotubes in that area.
Hold on 1 second, I'm going to count them. Actually, I shouldn't be touching these. Scientists don't yet know if they're toxic. Even so, there's already a rapidly growing market for nanotube particles as strength additives for tennis rackets, bicycle frames, even high-end car bumpers. Many products already incorporate carbon fibers, which are part carbon, part plastic. But nanotubes have greater tensile strength and toughness. Ray has set his sights on making super strong materials that are 100% pure nanotube, made from his nanotube forests.
These aren't just ordinary carbon nanotube forests. They are nanotube forests that have a very special type of connectivity between nanotubes. When we pull out one nanotube, that nanotube pulls out its neighbors, who pulls out other neighbors to self-assemble a yarn or a sheet.
Expert nano yarn spinner Kai Lewis gives me a hands-on lesson.
Would you like to try?
This I recognize. This is it. First, we start with a forest on a wafer.
So you can just grab on to this little orange tab.
Okay.
Now don't make it too high of an angle and make sure it doesn't touch the edge. And just pull up,
Fast or slow?
whichever you feel comfortable with.
Oh, dude. As I pull on this little tab, nanotubes are coming off the wafer, hooking other nanotubes and pulling them off the slide.
Try faster.
I'm so good at this.
At too high of an angle, it will, as this is now, it will start to break off from the forest.
It's like coming out forever. I'll see you at the Texas County line! It's still going. It's still going.
There, bro. And what's even neater, I can show you right here. I can even do a little twist
Wow,
and
you're making
make that into a yarn right here.
Insta
Look
yarn.
at that.
Wow.
It's about 1/100th of a human
Oh
hair.
my gosh, it is like steel. I'm pulling really hard. You probably can't even see that. In fact,
And it
look
will
at this.
stick.
It's so fine. You can't even see. Oh, that helps.
Keep twisting. Keep twisting.
Keep twisting. It's amazing.
It's stronger than steel.
Stronger than steel? So why then don't you take a bunch of these, twist them together, and make this super cable that'll be like bridge suspension cables and aircraft carrier cables?
Can you imagine spinning a bunch of these all day long to make into a rope that's a foot in
All right, so
diameter?
go the other way. Make the aircraft carriers really, really small.
Carbon nanotubes has already been implemented in many experiments on many forms of our lives. We already use them to make bulletproof suits that look just like regular suits. So if someone can shoot someone point blank range, they'd be fine. Aircraft companies are looking to use them because it's very lightweight and it's and is 200 times stronger than steel in tensile strength. I have a few more videos for y'all to watch.
This is a man-made rope.
A string. It can be woven into cloth or made straight into a high-stress component. These carbon fibre drive shafts are destined for very expensive road cars and Le Mans race cars. Manufacturers and racers need to know exactly how much stress a carbon fibre drive shaft can take. And this is the world of Chris Jones, a test engineer for a leading manufacturer.
So Chris, test engineer. I'm guessing that means you get to test things to destruction.
Yeah,
Pretty much. Because that's where I think you can help me. Because I know carbon fibre is used in Formula 1 because it's light and because it's strong.
yeah.
But how light is strong compared to other materials? And that's where you can help.
Well, all I did, we've got two prop shafts here.
Right.
I don't know if you want to pick that up.
So this is a steel prop
This is,
shaft.
yes. So
This big lump of metal connects the engines to the wheels, so
That's right,
all
yes.
power goes through this.
along the car, yeah.
Okay.
And here we've got the carbon fibre equivalent of the same thing. So if you want to pick that up and
Doesn't weigh anything at all. But I mean, obviously, if carbon fibre is as strong, if this is as strong as the steel one, it's a no-brainer because this is so much lighter. You need to use this.
exactly.
But can you tell me how much? So can you show me how much? If this is as strong as
I
that.
think we can do that.
What I'm asking is, can we break?
We can give it a try. Anyway.
Okay. Right.
This rig uses torque or twisting force to test materials until they break. Sensors can judge exactly how much force it managed to cope with before snapping.
So when this is working at full tilt and at full power, how much torque can you go through it?
So 8,000 newton meters we can put through with this rig.
It's really not the kind of device to catch a tide, is it?
To put this in perspective, it requires around 2 Newton meters of torque to drive a corkscrew into a wine cook. This rig can produce 8,000. It's a lot of clock.
So that piece of plastic and these glasses will protect us from the immense forces being unleashed.
That's the plan anyway.
Okay,
So, right.
Well, yes. We'll come back, maybe?
Okay,
Should be okay there.
so, right. Okay, well, next way, we see the numbers are arriving here.
293, that's a lot of Newton meters of torque.
It is.
This is twisting.
You can see if you look at this end, you can see this end of the machine will be twisting around.
So yielding already, look.
There we go.
That's the yield showing us.
That's the yield there, so the machine is about to fail, so any second now it's about to snap.
Really?
So this machine is just distorting now, you should be able to see it necking.
Necking, yeah, I know what you're thinking, but here it means when a material gets thinner in cross-section. It's an indication it's just about to fail.
Oh yeah, there it goes there! It's gone. I think we'll stop that there.
That's ruined.
I think it is.
Yeah, broken up. What did it make it to?
That got to 1,376 newton meters.
1300 Newton meters, and it's, well, it's now a corkscrew.
It is. Yeah, there you go then.
It's sucked the spring back in there. That is quite badly spoiled. Well, now to the limits for that one. Let's see what the carbon fibre equipment can take.
Okay, so we got that next.
That's a reminder of how much lighter this thing is.
Lighter, but in theory, much stronger. And much more expensive. £2,500 for this shaft alone.
It looks better, doesn't it? It does.
Power transfer arm.
I don't believe it's going to have any more strength compared with it still.
Okay, so we see what we can do at this one.
Right. So 1,376 is the target. If it can match that, it's matched the much heavier steel.
Yes, that's right.
Pile it on.
Good off.
So it's climbing 647, 8. It's never bad, this machine. This is 9, 10, 11. We're getting close to where the steel went. 13, well, it's just gone straight past. And there's no, completely blitzed.
There's no damage to the strap there whatsoever.
So there's much lighter.
Much lighter, much
It's
stronger.
just gone completely out of the park. What will it make it to you? I hope 4.5. 4.5 to 1300
Yeah.
steel, and it weighs so much less. 4 on the way to that, 4.2, 3, 4, 5. I was just about to ask what happens when it goes.
That's what happens now, guys.
I jump. So it made it to
It made it through 4,728 newton meters. 1300 steel.
and it's so much stronger than the big heavy steel one. Let's not forget, it's just made of this stuff, isn't it? Just threads, basically. It's just
Expensive real estate.
expensive strings. That's it.
Carbon nanotubes are can be like semiconductors, act like semiconductors. So here's a kind of sort of video on that.
Building up. As you can probably guess, the whole thing is pretty welding a metal called molybdenum to the ends of microscopic. Part of what contributes to the increase in performance we see with each generation of processors is the size of the manufacturing process. We've got the silicon process down to 10 nanometers, but below that point, processors start to generate too much heat. IBM thinks they've got a solution. The company is reporting a breakthrough in developing carbon nanotube transistors. Welding a metal called molybdenum to the ends of microscopic carbon nanotubes can keep the resistance low enough to prevent crazy amounts of heat building up. As you can probably guess, the whole thing is pretty complicated, so check out the source link in the description, but suffice to say, I'm pretty stoked for carbon nanotube transistors! Speaking of ridiculous technology.
And here's some application in muscle. Artificial muscles, if you will, carbon nanotubes.
Nanotech Institute at the University of Texas in Dallas have discovered that carbon nanotube sheets, also referred to as carbon nanotube aerogels, have properties unlike any other known materials.
Recently, we've discovered that we can make artificial muscles that can operate up to temperatures of above 1600 degrees centigrade, down to absolute zero on the Kelvin scale, and also they provide giant strokes. Like our natural skeletal muscle can contract by, in some cases, up to 40%, typically 20%. Our artificial muscles can undergo dimensional changes of about 220%. These muscles can operate extremely fast. For example, a natural muscle can contract at about 20% per second. Our artificial muscles can contract at about 30,000% per second. These new muscles are electrically powered. Artificial muscle action results from charge injection into a carbon nanotube sheet. This charge injection causes repulsion between the individual nanotubes, which causes giant strokes. These new artificial muscles are based on carbon aerogels that we make by drawing carbon nanotubes from a forest of nanotubes.
So there's a limb, stronger effect on muscles. Here's another small clip.
Which is something that we can handle on the macroscopic engineering scale for applications.
So what you're looking at here is two bundles of our nanotube fiber that are holding up an LED light bulb that weighs 50 grams. Those fibers are also being used to run the current that's powering the bulb. So this is demonstrating the multifunctionality of the fibers, that they are strong enough to support the weight of the bulb and also have high enough conductivity to provide the current.
This is just some fiber that I took off the drum, which was not under controlled conditions, but it's still good fiber. Just we don't know exactly what the conditions were, so we don't keep it. But you can see that it has a lot of strength. This thing is actually pretty heavy. This is the spinning cylinder. So we have carbon nanotubes that are dissolved in a solvent, which is chlorsulfonic acid. And this solution is a very viscous type of material, so it's kind of like mayonnaise almost in viscosity. And we're extruding it through 19 small holes and then winding it onto a drum.
This is a spool of the fiber. After it's been spun and wound, this is one continuous filament. So this was produced in a single spinning experiment where we spun a continuous filament and then we're able to wind it onto a spool like this. The machine we're sitting near here is the SEM, Scans Electron Microscope. And we use this to do high magnification imaging of the surface of our fibers so we can get an idea of what the structure is on a microscopic scale, the scale of a couple of micrometers or a few nanometers, tens of nanometers.
The cool thing about it is you have a material that's very strong and highly conductive, so it has properties of both metals and high strength materials like carbon fiber. But on the other hand, you can handle it like you would cotton, because it's essentially a textile material, not like a rigid material.
The main improvement that in terms of our process versus other work that's already been done on fabricating nanotube fibers is that if you use a wet spinning process as we've developed here, you have a very scalable process. So you can easily scale up to make more and more material without necessarily increasing your costs.
Syntegy makes Verran, which is one of the commercial brands of PPTA fibers. It's very similar to Kevlar. They used for high strength applications like ballistic protections. And because the method for making Verran is so similar to the method we use for making nanotube fibers, Teijin are interested into working with us. They are real artists in the art of fiber spinning, and they have been able to move the technology so much faster than we could have done just by ourselves.
That ends my presentation. Any questions?